So today we're going to be talking about area between curves, but we're going to start with a review of just evaluating definite integrals going back to 4.4, definition of a definite integral, because arguably we are just repeating that same concept with a little bit of an extension on it. Though I may verbally review some concepts, we're not going to be doing, we're only going to be evaluating area between curves. So our definition of a definite integral, again, the limit as n approaches infinity, the summation where I starts at 1 and goes to n of f of c sub I times delta x is equal to the definite integral from a to b of f of x dx. Then we got that's equal to capital F of x with an upper limit of b and a lower limit of a, finishing up with capital F of b minus capital F of a. What is capital F in comparison to or versus lowercase f? This is the integrand. F of x dx is the integrand. What's capital F? Antiderivative. Exactly. We find that antiderivative of f of x, lowercase f of x. We get our capital F. We plug in the upper and lower limits, and we get f of b minus f of a. What do you get from a definite integral? Just a number. It could be, what is the integral of v of t dt? Not that we're going to, I'm just reviewing some concepts. What is the integral of velocity? If I'm moving to the left, my velocity is positive or negative? Negative. And when I integrate velocity, when you integrate a rate of change, a definite integral, you get a what? Amount of change. So the amount of change, if I'm talking about an integrand that's velocity, I might be integrating velocity. I've started here where I'm at, now time 0, and then the timer starts and I'm moving to the left with a negative velocity. When the time stops and I do a definite integral, what is that number from the definite integral equal to? Displacement. If you do I usually don't say a definite integral, but when you do a definite integral of a rate of change, you get amount of change. And in terms of velocity, that amount of change would be labeled as displacement. My velocity might be positive. And that displacement is going to be negative, right? I'm some distance to the left of where I started from. Now, I might be starting here and my velocity is positive. If I integrate velocity, I get displacement. So time stops, I integrate velocity and I get my displacement. I'm some units to the right of where I started from. So my definite integral is going to be a positive or negative number? Positive number. I'm to the right. So like velocity is positive when you go to the right and positive when you go up. Velocity is negative when you go to the left or down. So you might get a negative displacement. You might get a positive displacement. A definite integral is just a number. And what that number represents will vary based on whatever this function is representing. But if you do a definite integral on a rate of change, you get an amount of change in something. Kinematic, I think that's what it's called. The definite integral from a to b of the absolute value of velocity is total distance traveled. So if time starts now and I've got a negative velocity and a positive velocity and time stops, the definite integral of velocity is displacement. I'm right back to where I started from. What's my displacement? 0. But if I'm integrating the absolute value of velocity, maybe I moved left 5 feet, I moved right 5 feet. My total distance traveled is 10. That total distance traveled would show up from this definite integral. So one more time, just definite integrals just give a number. That number can represent many, many, many things. But today we're only talking about area. We're really not going to be we're not utilizing the definition of a definite integral today. We haven't had a discussion about it for a long time. You do have to have this whole definition memorized for the AP test coming up and basically just, to have an understanding of calculus. C sub I is the number that you're putting into the function, and it's a plus delta x times I for a right Riemann sum. And it is a plus delta I times I minus 1 for a left Riemann sum. We did most of our Riemann sum work with rectangles and a left Riemann sum. Your delta x is going to be the width. In general, most Riemann sums are rectangles, but you can do Riemann sums with trapezoids. You can do Riemann sums even with parabolic curves, which we didn't cover in this class. But delta x is b minus a over n. b minus a is the horizontal distance between the upper and lower limit, and of course you see that in the definite integral notation. We are ultimately building up to area between curves. If f and g are continuous functions on a closed interval, the only requirement needed to do a definite integral, and f of g is greater than f of g for all x on a closed interval from a to b, then the area between two curves is going to be the definite integral of f of x minus g of x dx. I've got more thorough notes on a past video I've done for YouTube. This is just going to be like, we're going to see through the examples that you don't have to integrate just along the axis of x. You're also going to be integrating with respect to y when the question lends itself to that kind of problem. So first, let's just make sure we can evaluate some definite integrals and find some areas between curves. Let's just revisit what we did in the beginning of chapter 4. What is the definite integral between pi over 2 and positive pi over 2 of the sine of x dx?
0.
Why?
Because there's no distance for it to...
Yeah, we have not moved any, there is no movement between the lower and upper limit along the x-axis. And we can integrate with respect to y as well. We're going to do that by hopefully the end of the period. And that's one of the properties of definite integrals. If your lower and upper limits are the same, the definite integral is equal to 0. So maybe I just forgot to, miscopy this problem. No, I wanted to review one of the properties of definite integrals. All right, so let's change the question a little bit. What if the lower limit is negative pi over 2? What is the definite integral between negative pi over 2 and positive pi over 2 of the sine of x dx? Anybody know an answer right away? These are the multiple choice questions that you should be hoping for in early May when you take the AP Calc exam.
I think it would also be 0.
Why is that?
It would be negative cosine
No.
pi over 2.
You're going to, why is it 0?
Oh, because it goes the same distance into the negative as it does positive.
That's not going to be the case for every type of function in our integrand. So can you be a bit more specific? It's an odd function. Okay? The sine function is, you got the correct answer. I just didn't want to talk about the calculus yet, like the actual calculus work. I don't like where I drew that. That's okay. I'll put the work over here. The sine function at pi over 2 and negative pi over 2, of course, the range of sine goes from 1 to negative 1. And if you graph y is equal to the sine of x, this is an odd function. All but 4 of the 6 trig functions are odd. Cosine and the reciprocal of cosine, which is secant, are the only 2 even trig functions. The sine of 0 is 0, the sine of pi over 2 is 1, the sine of negative pi over 2 is negative 1. And that's a graph of the sine function between, let me sketch, of the sine function between negative pi over 2 and positive pi over 2. So in chapter 4, when we were seeing this content for the first time, I might have said, and it's a little bit of a fib, a little bit of a lie, I might have said that this area is positive and this area is negative, because you don't know that much stuff yet. There is no such thing as a negative measurement. You cannot measure a negative length. You cannot measure a negative area or negative volume. That doesn't really exist. So when you talk about measurements that end up taking like a positive or negative value, velocity moving to the left is negative. Displacement moving to the left is a negative displacement, indicating you've moved to the left. So like, this is a positive area because it's above the x-axis. This is a negative area because it's area below the x-axis. You can think of the positive, negative nature of the area as just a directed idea of being above or below. Of course, definite integrals give you numbers that can, that can apply to all kinds of situations. And going back to, this is part of the reason I wrote out the definition of a definite integral. Delta x is a width, and yes, you can do Riemann sums with more than just rectangles, but delta x is a small movement along either the x or y axis. It's sort of like the base of the rectangle, at least for a rectangular Riemann sum. And the height of those rectangles is coming from the function. That's your f of c sub I. And if your function is giving negative answers, then you're going to have a positive width times a negative answer giving a negative answer. Definite integrals have given us negative answers many, many, many times. But when we're saying the word area, area by strict definition cannot be negative. So we're kind of just sort of fibbing a little bit and making the, sort of this new content palatable in chapter 4 when we were finding area. You know, and I said in chapter 4 it was like directed area. So the sine function is an odd function, and the lower and upper limits are opposite values. So that is another property of definite integrals. When your integrand is an odd function and your limits are opposite numbers, you don't need to evaluate the definite integral. It is 0. Now, I can say it's 0, or I can do what did in his head. You know, he worked the math, and you'll still get the right answer. You just won't get done as quickly. So we have some Riemann sums. Some of our rectangles are above the x-axis, giving us positive function values, giving us positive, you know, quote unquote area. Some of our Riemann sums, some of our rectangles that we're, you know, finding the sum of has a positive delta x and a I'm not losing place of where to write here, and a negative function value because the function's below the x-axis. But yeah, the integral of sine is negative cosine. We have that upper limit of pi over 2 and negative pi over 2. We plug those in, negative cosine of pi over 2 minus a negative cosine of negative pi over 2. And this is not the most exciting question. What's the cosine of pi over 2? Cosine's the x-coordinate. My shoulder's the origin. That's 0. So negative 0 plus negative and negative is positive. We're not getting an answer. We're not going to get an answer of 0 because the cosine of pi over 2 is 0. We're getting an answer of 0 because cosine's an odd, because the sine function is odd. So maybe this isn't the best example, but negative and negative makes positive, and the cosine of negative pi over 2 is 0. And negative 0 plus 0 is what we knew in the first place because we know that this integrand is odd and these limits are opposite. Our answer is 0. So for example number 2, still, so a little bit of recall back there that in our earlier sections we have stated that quote unquote areas were negative. That's not really a true statement. Area by definition must be positive. The only reason that we said an area was negative is because it was below the x-axis. So for our next example, we've got find the area between this parabola negative x squared plus 4x. You know, find the area between this parabola and the x-axis. Well, how do I know this is a parabola? I just sort of gave it away, but how do we know this is a parabola? You got a square. You have one squared term, and the leading coefficient is negative. So what direction is this parabola opening? Down. So you are going to ultimately, to do 7.1 well, to find area between curves accurately, you're going to need to start with a graph. So let's find out where this graph crosses the x-axis. So we have negative x squared plus 4x is equal to 0. Let's factor out a negative x and get negative x times x minus 4 is equal to 0. And we have x is equal to 0 and x is equal to 4. What is the multiplicity of these zeros? Now, if you know parabolas and you know this is opening down, like I'm asking you questions that maybe you don't need to ask for this particular question, but for more advanced problems, you might need to. You probably do need to. What is the multiplicity of x equals 0? Do you even know what I'm talking about with multiplicity? It's how many times did the factor that this 0 came from show up? So this 0 came from this factor, which showed up one time. This 0, this solution, showed up from this factor that occurred in the equation in factored form one time. I'm going to have to erase this because I have a feeling that you don't remember any of this from last year, and I wasn't your teacher last year. So you need to have this, well, in my mind, you need to have this down. If you know multiplicity of zeros for polynomials, you can make some calculus questions go quite quickly, especially multiple choice where you don't have to show your work. And even some FRQs. If your multiplicity is odd, the graph passes through the x-axis. And if your multiplicity is even, then the graph touches the x-axis. So you probably would have realized, you don't have to really think about that for this question because it's a parabola, but that is going to pay off benefits, I believe, in the future as we review now for the next basically 2.5 months for the AP test or whatever is left. I'm not going to worry about the vertical scale, so let me just take that out. The location of the vertex is really not important. But we do have an x-intercept at 0, and we're going to pass through the x-axis because that has a multiplicity which is odd. We have an x-intercept of 4, and that also has an odd multiplicity, so the parabola is going to pass through the x-axis. And it is opening down, so the graph, I don't need to know where the exact location of the vertex is other than it's above 2. Looks like this. And we are asking for the area between the parabola and the x-axis. I promise we're about to get into chapter 7 here, toot sweet, very quickly. How do we evaluate this area? How do we find that area? You've done these questions many, many times. We haven't specifically had the direction of find area recently, but we've done it a bunch. So the area is going to be the definite integral between what and what?
0 and 4.
Okay. What's the integrand?
The function.
The function, so negative x squared plus 4x dx, and then let's get going. That's correct. So integrating using power rule, x to the 1/2 is going to become x cubed divided by 3. So we have negative 1/3 x cubed plus power. This is x to the first, so the x comes up. We have x squared divided by 2. So we have 2x squared, upper limit of 4 and 0. Now we have negative 1/3 times 4 cubed plus 2 times 4 squared. Please make sure that, please help me out if you see me write something silly. We got the upper limit plugged in. Now we're going to do the lower limit. So we have negative 1/3 times 0 cubed plus 2 times 0 squared. Don't be too jumpy about, oh, I'm plugging in 0, the answer is going to be 0. I can't tell you how many times I've done that, but what's the cosine of 0? 1. What's e to the 0? 1. I mean, like, sometimes when you plug 0 into a function, you don't get 0. So that, we're not trying to make mistakes on purpose, but that has definitely tripped me up at times. So we have negative 64 over 3 plus 4 squared is 16 times 2 is 32 over 1. This does come out to be 0. Find a common denominator and get a final answer of 96 minus 64 is 32? Yeah, okay. So we got 32 over 3 square units because we're specifically talking about area. Y takes a little longer to teach by discovery, but I hope it makes for better understanding. Why is this the area? Why does the area stop at the x-axis? No one questioned that in chapter 4. If the area doesn't stop at the x-axis, you're just finding the area below the curve between 0 and 4, and that area is going to be like infinite. We have to make this a little bit palatable. You know, calculus is hard, and so we're trying to teach you in small stages and then reveal some of the truth later. You did not actually find the area just under one curve. You've already been finding the area between two functions, which is what 7.1 is about. That's the title of today's lesson, finding the area between curves. This is not the area under the parabola. The area under the parabola between 0 and 4 is infinity. It's the area between the parabola and the x-axis. And we just sort of let you sort of think that the area always just stops at the x-axis, 3 chapters ago. But you're really not finding the area between or under one curve. You're finding the area between two curves. There's a second curve in this problem that I never pointed out to you in chapter 4, because, you can't learn everything in one day. The other curve is right here. Your second curve is y equals 0. Going back to the definition of a definite integral, your Riemann sum, and we drew Riemann sums, we drew rectangles. Those rectangles always stopped at the x-axis. So really, what you did was not the definite integral between 0 and 4 of negative x squared plus 4x dx, even though that's all we wrote. Now we need to realize that what we really were doing was the definite integral from 0 to 4 of negative x squared plus 4x minus 0. And when we said, how tall is this representative rectangle? Okay, I'm kind of unintentionally drawing midpoint Riemann sums. But when we did those Riemann sums, every rectangle had a new height based on the functions that it was between. So it was the y value from the parabola minus the little y value from the line. And the big y value from the parabola, if it was above the x-axis, minus the little y value from the line, and so on and so on. So when you set up a definite integral to find the area between two curves, it is the definite integral of a big Y minus a little y, so that you get a positive difference, a positive distance between the two functions. And of course, the answer is still 32 over 3. Now, if we take this problem and we shift it a little bit, maybe we say that for another example, maybe we want to find the area between f of x is negative x squared plus 4x plus 2 and g of x, which is, another y is equal to 2. I just took this vertical line of y equals 0 and shifted it up 2 units. I just took the parabola of negative x squared plus 4x and shifted it up 2 units. So basically, instead of this being the x-axis, I wish I used green. This is y is equal to 2. And this is sort of a sketch of our situation. There's a y-axis, and then 2, 1, 0. Here is our x-axis. And by the way, I could shift the graph up or I could shift the graph down. What's the distance? How many markers can I hold in my hand at one time? What's the distance between 10 and 5? 5. What about 6 and 1? 5. What about 3 and -2? 5. What about -1 and -6? So if I move a system up and down, it doesn't matter if the whole system's above the x-axis or split by the x-axis or below the x-axis. It's not going to change the distance between the two functions, at least not if they're shifted the same. So how are we going to find the area between these two curves? Well, number one, every question about finding area needs to be set up with a picture first. So you're going to graph this parabola. You need to graph the parabola, and it can just be a sketch. All you need to know is what function is giving you the bigger y values or the smaller y values, and then if they intersect on a closed interval. So how do we find the vertex of this parabola? We haven't done that in a minute. There's many ways. You can complete the square and put this in vertex form, or you can do the x-coordinate of the vertex. It's the first term of the quadratic formula. The x of the vertex is negative b over 2a, which is -4 over 2 times 1, which is, this is really shocking. That's, oh, a is -1. Woof. I was like, wait a minute, this isn't working out right. 4 divided by 2, shocker, that's a 2. What is the y of the vertex? Well, f of 2 is going to be -2 squared plus 4 times 2 plus 2. So we have -4 plus 8 plus 2, which is 6. Okay, so this parabola has a vertex at 2, 6, and it opens down. This parabola opens down, you know, it's somewhere, I don't know where it's at, but the vertex is at 2, 6. Now here comes the line, y equals 2. So here comes your other graph, your other function, y equals 2. I don't really know what this is, it's just a super rough sketch. Y is equal to 2. That's a terrible sketch. Where do these graphs intersect? Okay. That's step number 2. Graph step 1. Step 2, where do these functions intersect? Well, you're going to set these two functions equal to each other. Just like you did over here. Why did we set this parabola equal to 0? Because we were finding x-intercepts. We were finding out where this function equals. What's the equation of the x-axis? Y equals 0. We were setting the two functions equal to each other. So we're going to set these two functions equal to each other. And numbers will start looking very similar very quick. So let's find, here's the graph, step number 1. Step number 2, where do they intersect? Where do the two functions intersect? So where does -x squared plus 4x plus 2 equal 2? Oh, that's -x squared plus 4x is equal to 0. Oh, we already did this problem. That's going to happen at x equals 0 and x equals 4. So to solve example number 2, your definite integral is going to be, the area is going to be the definite integral between 0 and 4 of, there's your representative rectangle. Which function has given us the big Y? What's at the top of this rectangle? The parabola. The vertex. Dude, we're going to have rectangles of different lengths all over the place. That height is going to be variable. So where is the top of these representative rectangles that we would have been drawing back in chapter 4 with Riemann sums? It's at the parabola. Okay? And the parabola is your -x squared plus 4x plus 2, that's your big Y, minus your little y. Where do all these parabolas stop at? at y equals 2. And of course, now I'm going to stop because this area is going to be the definite integral between 0 and 4 of negative x squared plus 4x. And what's 2 minus 2? 0. So we're right back to where we started in the first place. So you have already been doing the math needed to complete 7-1 successfully. Granted, you know, situations will become a little bit more complicated. But sketch, find the intersection points, and then based on the intersection points, those points become the limits of your definite integrals, and your integrand is always a large value minus a small value. It might be a big Y minus a little y, or it might be a big X minus a little x. But it's a large value minus a small value. Now, when you have vertical rectangles in your Riemann sum, you're going to be integrating with respect to x. That's why there is a dx. But when we lay our representative rectangles down horizontally, your little delta x's are going to become little delta y's. We good with this? Everybody okay with this? Yeah? Totally good? Okay, let me get this erased, and I think I can get one more before the bell rings. Find the area between y is equal to negative 2/3 x times x minus 6 and y is equal to negative 1/2 x plus 11 between x equals 0 and x equals 6. It will not be every time, but a lot of times when they give you a boundary between which you will find the area between two curves, there's actually a fairly decent chance that those two curves will not intersect. If there is an intersection between those two curves, though, you are going to have to set up multiple definite integrals. We want to find the area between two curves. What's the first step? Graph them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 4, 6, 8. So y is equal to negative 1/2 x is somewhere looking like this. Just a sketch, okay? We just have to know what function is giving the larger y values in this case and which one's giving the smaller y values, so we set up our integrand correctly. Our other function, which I'll have in blue, let's go ahead and let's temporarily leave this in factored form. Y is equal to negative 2/3 x times x minus 6. Where are our x-intercepts? X equals 0 and x equals 6. Okay, without work because we're at the end of Calc 1, right? So we have x-intercepts of 0 and 6. I don't think it's going to happen, but what we do not want this parabola, well, if it does happen, we need to understand it and take care of it. If that parabola goes up above that line, you're going to have to set up 1, 2, 3 definite integrals. And I'm hoping the question is not that involved. So we need to find the vertex. So let's take this parabola, distribute the negative 2/3 x, and get y is equal to negative 2/3 x squared minus 6 divided by 3 is 2, times 2 is negative 4x, unless I've made some silly mistake. Is that good? Oh, plus. I did make a silly mistake. And you can put this in vertex form by completing the square, but I think I'm going to just stick with the negative b over 2a. The x of the vertex is negative b, so negative 4 over 2a, 2 times negative 2/3. So we have 4 over 4/3, which when we multiply by 3/4, we're going to get an answer of 3. So the x-coordinate of the vertex is 3. and plugging that back into the function just to make sure that, our sketch is going to be good. We have y of 3 is negative 2/3 times 3 times 3 minus 6. So we have 3 divided by 3 is 1, so we have negative 2 times negative 3, 6. So this parabola has a vertex at 3, 6. Okay, so we are way below the line. And we want to find the area between 0 and 6. I want to find the height of this rectangle, or even, you could even call it a line segment. How do I find the variable height of that line segment, giving only positive answers? What's the big Y coming from? The line or the parabola? The line. Where's the little y's coming from? The parabola. So when we set up our integrand, it's going to be line minus parabola. So that when we have a bunch of representative rectangles, they're giving us positive area. We have an area is equal to the definite integral between 0 and 6 of the line of negative 1/2 x plus 11 minus the parabola, which is negative 2/3 x squared plus 4x dx, which means that's going to clean up to be a definite integral between 0 and 6 of 2/3 x squared, I'm just going to start copying off my notes because of time, minus 9/2 x plus 11 dx. That is going to yield 2/9 x cubed minus 9x squared plus 11x with an upper limit of 6 and 0. Expanding that out, plugging in the upper and lower limit is going to yield us an area between those two curves, like I stated yesterday, of 33. It's just 33 square units. It's just that there's the work actually written out. So if you needed that, take that down. I'm going to erase this and put up our next example. Find the area between these two curves. I'm starting to realize if there's not something on the whiteboard, it starts freaking out on the focus. Find the area between these two curves. What did I tell you yesterday was the first thing you need to do when finding the area between two curves, Maya? Draw them. So we've got a line in standard form, which I don't really want to work with. So we have y is equal to 4x plus 12. So I added 4x to both sides. Again. So we've got a line with a y-intercept of 12 and a positive slope. So we have a line that, without scale. This is just a sketch. And then we have a cubic function with a positive leading coefficient. So what is the end behavior of this cubic function? Yeah, it's down to the left, up to the right. The limit as x approaches negative infinity is negative infinity. The limit as x approaches positive infinity is positive infinity. The end behavior of this cubic function is going to be down to the left and up to the right. How many turns do cubic functions have up to? You might not see any. Up to 2. So this cubic function, now right now we don't know if this cubic function, okay, which I'll do in yellow and I'll do in orange. I don't know if this cubic function looks like this, or looks like that. I don't know if these two functions, where they intersect, but we do have to find the area between the two functions. See, this problem, unlike the one that we just did, there's no limits defined. It's not find the area between 0 and 6. So these functions are going to have to intersect somewhere so we can find the area between them. We just have to find out where they intersect. And spoiler alert, it's going to be the one in the middle. But we're not going to know that without doing some algebra. So let's figure out how to determine that basically what we're going to do is find the area of these two regions and add them together. But these are going to be non-calculator questions. So you're not going to be able to just type these in your calculator and see them. but we have to understand, the general behavior of each of these functions, find the intersection points, and then we should understand from there what the situation looks like. How do we find out where two functions cross? How do we solve a system of equations? Yeah, set them equal to each other. They're both set equal to y. So we've got step 1 is to draw. Step 2 is look for any intersection points. So we're going to be setting these functions equal to each other. We have 4x plus 12 is going to be equal to x cubed plus 3x squared. Moving everything to one side, and I don't like to factor when my leading coefficient's not positive. It's not a mandatory thing. It's just my personal preference. So I'm going to bring the 4x and the 12 over with subtraction, and just so I have a place to normally stand where I like, I'm going to keep everything on the left hand, ultimately have everything on the left hand side. So subtract the 4x, subtract the 12, and we have x cubed plus 3x squared minus 4x plus 12. This is not an inequality, it's an equal sign, so to swap both sides is sufficient. Okay, so I confused you. Oh, myself, minus 12. Yeah, that's a positive, so I'll bring it over with subtraction. Now, when you have higher order polynomials, you pray that they actually factor, because otherwise they're a huge pain to solve. And to give you, something to look forward to, they're not going to try and bury you under a ton of algebraic work on the AP test in general. They're testing your knowledge of skills. Is everybody okay with that? Okay. So hopefully this factors. What can we factor out of the first two terms? X squared. So an x squared comes out, giving us x plus 3. We can take a negative 4 out of the last two terms, giving us negative 4 times x plus 3. That's equal to 0. And now we have x squared minus 4 is then as a factor times x plus 3. This can factor again, and we have x plus 2 times x minus 2 times x plus 3 is equal to 0. So I don't need the full-blown intersection coordinates. We need to find either just all the x values or all the y values where the two graphs meet. So we have an x-intercept, we have an intersection between these two functions at negative 2, at positive 2, and at negative 3. Now, we've got negative 2. Nope, we got negative 2. We've got another intersection point at x equals negative 3, and another intersection point at x equals 2. This has to be the orientation because of the end behavior. We got an odd degree polynomial with a positive leading coefficient. This is the end behavior, and there can be up to 2 terms. So this has to be the orientation of the graph. So for region 1, what is the, and we're going to have to think about this, and maybe I'm getting ahead of myself, but between negative 3 and negative 2, what function is going to give us the big Y? The cubic function. Probably should have given these different names, but the cubic function. So we're going to we need to find the distance between these two functions, along every value of domain of interest. And in the first region, the cubic function is going to be on top of the line. So the big Y is going to come from the cubic function. But then between negative 2 and positive 2, that cubic function has taken a turn and fallen below the line. So in region number 2, hopefully these colors show up. We'll do this in blue, so definitely will. In region number 2, we're going to have to find, those representative rectangles. Like we started by reviewing Riemann sums a little tiny bit, the definition of a derivative the other day. We need those areas to be positive. We need the length of that line segment, the distance between those two functions, to be positive. What's the big Y value going to come from in region 2? The line. And the small y value now is coming from the cubic function. So if we want to find the total area trapped between these two curves, we need to recognize where they intersect and which function is on top, which function is giving us the big y values for now, because we're going to integrate with respect to x. When you have, or when you've decided to find the area between curves using, representative rectangles that are vertical, you are going to be integrating. Those are a bunch of little delta x's. You're going to be integrating with respect to x. Our next example will be a little different. Okay? So our area between these two curves will require two definite integrals. Okay, we're not finding like the sum of the areas where like some areas are positive and some areas are negative. Like we started yesterday reminding you, like when we had area below the x-axis, it was quote unquote negative because it was below the x-axis. Well, definite integrals don't just give area. They give all kinds of, they give numerical values that represent all kinds of situations. But when you're calculating area, area is positive. All real-world measurements, length, area, volume, have to be positive. So we're doing a definite integral from -3 to -2. And from -3 to -2, one more time, what is giving the big y value? The what? The cubic function. So we're looking at x cubed plus 3x squared minus the little y value. The little y values, this line segment stops at the line. So the little y values, the variable y values are coming from the line. So it's the cubic function minus the line. It's the cubic function x cubed minus 3x squared minus 4x plus 12. And then you're going to add that. That's going to be the area for region number 1. Now we have to do another definite integral for region number 2, where the line ends up giving you the larger values and the cubic function gives you the smaller y values. So we have that plus the definite integral from -2 to 2 of, one more time, the big y value. I know I just said this, but in the second region, the big y value comes from what? The line. So 4x plus 12 minus, in region 2, the little y, the bottom cubic function. So minus x cubed plus 3x squared. So this looks like a nice little innocent problem, and it's not that bad because everything's polynomials, but here's a couple of polynomials. Basically, find the area between them. Well, integrating a polynomial just involves power rule. That's easy, but yeah, this is going to be a lot of work. It's a lot of simple work, but a lot of work. So, which I'm going to just sort of shut up here in a minute and start writing so we can kind of get this done quickly and move on to something more interesting. This is a good, interesting problem because it's your first example of two functions intersecting and finding area without a defined boundary. But the amount of work it's a little bit much. So x cubed, the definite integral from -3 to -2 of x cubed plus 3x squared minus 4x minus 12 dx plus a definite integral from -2 to 2 of, distribute the negative, and we have negative x cubed minus 3x squared plus 4x plus 12 dx. That's going to be then 1/4 x to the 4th plus x cubed, because you raise that power up by 1 and then divide, so you're going to have just a 1x cubed. Raise x to the 1st up by 1, but then you divide, so you have minus 2x squared minus 12x with that upper limit of -2 and a lower limit of -3. And then plus negative 1/4 x to the 4th minus x cubed plus 2x plus 12x with that upper limit of 2 and lower limit of -2. And I'm just going to copy this down, and I'm not going to show every single step of simplification. We're at the end of like calculus 1. But just for notes. No, this is longer than you'll have. This is a time suck now, to be honest, right? So I'm plugging in the upper limit of -2, so -1/4 times -2 to the 4th times -2 cubed minus 2 times -2 squared minus 12 times -2 minus, now you're just repeating the process, but now plugging in -3. And we're going to add that to doing it again, but now with an upper limit of 2 and a lower limit of -2. Oop, I missed a square. Y'all didn't help me there. 2x squared. Oh. Okay, let me pause, make sure I copied this right. And that comes out to be 131 over 4 square units. So you'll have a question like this, and we have one coming up at the end of the notes. Hopefully we can get it done in 15 minutes. That is the same idea, but with a lot less like mechanical work. But when, again, asked to find the area between two curves, sketch, find the intersection points, and then set up the definite integrals. Something with this gross amount of work on an AP test may simply be just set up the definite integrals. Or it'll be a calculator-based question. Because this is, you're never going to get buried under that much arithmetic. Okay. So this is either just a setup problem to be in reality or a calculator-based question. But that is how this process works. So we got find the area between y is equal to x plus 1 and y squared is equal to 2x plus 10. Number one step, graph. Okay, well, we've got a parabola opening sideways. That's going to be a little bit of extra, an extra layer of difficulty on this problem, but it honestly is not that hard of a question once you get past the fact this parabola opens up sideways. So how are we going to graph this parabola? And how do we even know this parabola opens up sideways? Yeah, because the y is being squared, not the x. So you have one of two things. You can either write this into vertex form, which is to say we've got y squared is equal to 2 times x plus 5. And vertex form from Algebra 2 or might have been called standard form in pre-calc, depends on the textbook you're using. This is y minus k squared is equal to 4p, I think is what that coefficient is. Hopefully I don't have to edit that in the video. Times x minus h. So this is a parabola whose vertex is at -5, 0, and because the y is being squared and there's a positive coefficient on that squared term, this parabola is opening to the right. Now you have another option, which is to, when we have parabolas that open up or down, it's the single degree term that's isolated. So if we realize that this parabola opens now to the right because it's the y squared, you could solve it for x. And you can take this now and say that, well, y squared is equal to 2x plus 10, which means we have y squared minus 10 is equal to 2x. And then giving us, after we divide everything by 2, we have, and just because I don't have much room over here, I'm going to again swap the sides of the equation. Divide by 2, we have x is equal to 1/2 y squared plus 0y minus 10. And I'm doing it that way, writing the 0y because, again, the x, or in this case it'll be the y of the vertex is going to be the opposite of b over 2a, which means the y of the vertex is going to be opposite of 0 over 2 times 1/2, or again 0.
Anna also said that.
Too bad I didn't hear. And then so dividing by 2, we have that minus 5. I'll get you, D. You deserve that too. All right. So however you look at it, this system of equations is going to look like this. We have a line whose y-intercept is 1 and a slope of 1. So we have a line that basically looks something like this. And we have a parabola, which I'll keep in blue, that has a vertex at negative 5, 0 from however you figure that out. And that's going to be to the left of this x-intercept of negative 1. So we need to find the area between these two curves. Now, if you draw vertical representative rectangles, and you have a homework problem that's specifically asking you to do this to make you struggle through the pain in the buttness that it is, you're going to, if you want to integrate this, if you want to do this problem with a bunch of little vertical representative rectangles integrating with respect to x, then you're going to have to set up two definite integrals. Because in the orange region, you have a parabola on the top half and a parabola on the bottom half. And that parabola is going to be in the form of y is equal to plus or minus the square root of 2x plus 10. And you're going to be doing integrals with radicals, which are always so much fun. You'll also then have to set up another definite integral for when you have a parabola setting up the upper big Y and the line representing the lower Y. So this problem, finding the area between these two curves, keeping representative rectangles that are vertical is not fun. If you want to do this problem with and again, I'm trying to remind you of the Riemann sums we learned in chapter 4. The math is up here. Then you're going to only have to set up one definite integral. There'll be a bunch of representative rectangles laid down on their side, which means that is a bunch of small delta y's, not delta x's. And you will be able to do this problem in only one definite integral. All right? Because on the entire left-hand border of this region, you have a parabola, and on the entire right-hand border of this region, you're going to have a line. And if we were doing Riemann sums, all the representative rectangles would be defined by those two functions. So let's see what that looks like. I already erased the examples, but when you're integrating with respect to x, you have to have y in terms of x. When you're integrating with respect to y, you need x in terms of y. We got the sketch. What's next? Intersection points. Set these things equal to each other. Do we need values of x or values of y? These are stacked vertically from a low y to a big Y. We need to find the y values where these functions intersect, not the x values. So both of these functions need to be written x in terms of y. Right there. That's right there. We're going to integrate with respect to y. Our functions need to be or need to have independent variables of y. So this is a new one for us. We haven't done one of these. So don't space out on me. Y is equal to x minus x plus 1 is going to become y minus 1 is equal to x. And I'll keep the parabola in blue. Y squared equals 2x. I've already done this, but y squared is equal to 2x plus 10 becomes y squared minus 10 is equal to 2x. This time I'll try to remember to divide the 10 by 2. And that's x is going to be equal to 1/2 y squared minus 5. And let's set these equal to each other. So setting these equal to each other, we've got y minus 1 is equal to 1/2 y squared minus 5. And now I kind of regret creating a fraction, so I'm going to undo that. How do I undo the division of 2? Multiply 2y minus 2 is equal to y squared minus 10. So we have 0 is equal to y squared. Bring the 2y over with subtraction. Bring the 2 over with addition. So negative 10 plus 2 is negative 8. And we get 0 is equal to y minus 4 times y plus 2. So intersection points are y is equal to 4 and y is equal to negative 2. This y coordinate is negative 2, and this y coordinate is equal to 4. Our area is going to be a definite integral from negative 2 to 4 in a horizontal distance. If you went from 4 to 7, how far did you travel? 3. Did you do 4 minus 7 or 7 minus 4? 7 minus 4. Big X's are on the right. Little x's are on the left. This is a big X. This is a little x. Where are the big X's coming from? The line. The line which is defined as x is equal to y minus 1. So big X, y minus 1, minus little x. Where are the little x's at? The parabola, defined as x is 1/2 y squared minus 5, dy. So now we're looking at, let me double check my work. Yeah. So we have the definite integral from negative 2 to 4 of negative 1/2 y squared. This is a positive y, so plus y. Distribute the negative. We have 5 minus 1, which is 4, dy. And power up and divide. So y to the third, divide by 3. We have negative 1/6 y cubed plus power up and divide, 1/2 y squared plus 4y with an upper limit of 4, a lower limit of negative 2. And we have negative 1/6 times 4 cubed plus 1/2 times 4 squared plus 4 times 4 minus, parentheses, now plug in the lower limit. We have negative 1/6 times negative 2 cubed plus 1/2 times negative 2 squared plus 4 times negative 2. And when you get done with your arithmetic, that's going to come out to be 18 square units. Okay, just you and me now. For our last example, we are going to find the area between f of x is equal to 2 times the sine of x and g of x is equal to the square root of 2 times the tangent of x. And let's see what these look like. So let me go ahead and in blue do a quick sketch of y is equal to, or f of x is equal to 2 sine of x. And that look like so. We got the sine of 0 is 0 at pi over 2. We have sine coming in at a value of 1. And at negative pi over 2, we have a sine value of negative 1. And we have this graph. And we're going to find the area between these curves between the interval of negative pi over 4, positive pi over 4. Okay, so here's our sine wave looking something to this effect. It's an odd function, and we might be able to take advantage of that here in a minute. Then in red, we got g of x is equal to the square root of 2 times the tangent of x. So the tangent of 0 is 0, and we know that the tangent function is undefined at pi over 2 radians because you're going to have a y value divided by an x coordinate of 0. So we have a, unless of course you have a period change or some kind of phase shift transformation on your graph, we just have an amplitude change. So this center portion of this tangent function are going to have vertical asymptotes at x is equal to negative pi over 2 and x is equal to positive pi over 2. And we know that basic shape of tangent. It's asymptotic here, and it kind of swings around and sort of makes a very elongated S shape. So it seems like there's a possibility for some area, and there, if there isn't any, this would be a very terrible question, but it seems like there's going to be area between these two curves, trapped somewhere. Now we need to find out where these curves intersect within this closed interval of negative pi over 4 to positive pi over 4. Hopefully, just having two regions to find the area of an add, and not actually 4 because they cross, 3 times on this closed interval. So let's see what happens there. We drew the picture, and we're going to be having representative rectangles that are going to be fashioned vertically. So I can tell just by drawing the picture that we're going to have a lot of delta x's, and we're going to be integrating with respect to x. So when we find our intersection between these two functions, we're going to be solving for x. Let's see what that looks like. We're going to set these functions equal to each other. Basically, y is equal to 2 sine of x, and y is equal to the square root of the tangent of x. So 2 sine of x equals the square root of 2 tangent of x. We're going to get this equation set equal to 0. So we have 2 sine of x minus the square root of 2 times the tangent of x is equal to 0. And we have one single equation with two different trig functions. That is potentially going to be unsolvable unless we can create two factors or factor this equation so that each factor only holds one trig function, thus each factor only has one variable. So the tangent of x is going to be sine of x over cosine of x. So 2 sine of x minus the square root of 2 times the sine of x over the cosine of x is equal to 0. And at this point, you have two choices. You can either multiply both sides of this equation by cosine of x, which I think I'm going to go ahead and do, or and see what kind of factoring we can do. Or we can factor a sine out of these two terms as it stands, and which is actually what I did in my notes, and work off of that. But I'm going to multiply both sides by the cosine of x to get that cosine function, that variable, out of the denominator. And we end up with 2 sine x cosine x minus the square root of 2. The cosine of x times sine of x over cosine of x with that coefficient of square root of 2. The cosines are going to cancel out, so minus square root of 2 times the sine of x is going to be equal to 0. And now we have two terms, and we had it up here as well, but we have two terms that both have a common factor of sine. So we're going to go ahead and factor out that sine and have the sine of x times 2 times the cosine of x minus the square root of 2 is equal to 0, and set each of these factors equal to 0 and solve. So we have the sine of x is equal to 0, and this equaling 0, adding by square root of 2 and dividing by square root of 2 is going to yield the cosine of x is equal to the square root of 2 over 2. On this interval from negative pi over 4 to positive pi over 4, the sine of x is equal to 0 at just 0. So there is the intersection point between these two functions that we could see, obviously from the graph. And then the cosine of x is going to be equal to the square root of 2. Now on the unit circle, remember our defined domain here that we're trying to solve this solution for is x is going to be between negative pi over 4 and positive pi over 4. So we're looking for angle measures that are in quadrant 1 and quadrant 4. So the cosine of x being square root of 2 over 2, that's going to occur at negative pi over 4, and x is going to be equal to positive pi over 4. So that's a nice convenient match that goes along with our closed interval on which we're finding the area between these two curves. You saw in our previous example that when you have limits that are opposite numbers and you're working with an odd function, that area is going to be, or that value of the definite integral is going to be 0. Not area, but the value of the definite integral. But we're finding the area between two curves. It's not like we have a quote-unquote negative area for sine between negative pi over 2 and 0, and between 0 and positive pi over 2, and the same, of course, would be true for negative pi over 4 to positive pi over 4. It's the area trapped between the tangent function and the sine function. So we could do one of two things. We can find this total area by doing a definite integral from negative pi over 4 to 0. And as we try and find the height of our representative rectangles, we have to do the big Y over the little y. Well, in between negative pi over 4 and 0, the tangent function is the function on top. The tangent function is the one that's giving the bigger y values, and the sine function is giving the ones giving those smaller values. So we would have a definite integral from negative pi over 4 to 0 of big Y coming from the tangent function. So square root of 2 tangent of x minus the little y coming from our sine function. So minus 2 sine of x dx, and then with that adding another definite integral from 0 to pi over 4. And over here between 0 and positive pi over 4, now the sine function is on top. So we have the sine function giving those large y values and the tangent function giving the smaller ones. So we have, marker down. We have 2 sine of x minus square root of 2 tangent of x dx. So while we can do all of this, we can still take advantage of the symmetry that's going on in this graph, because both our 2 tangent of x and our square root of 2 tangent of x, both of these functions are odd, and our limits are basically going, we have opposite limits going from negative pi over 4 to positive pi over 4. So we can actually take advantage of the symmetry, do the integral or find the area of just one of these regions and double it. That's always nice too. So, in your algebras and pre-algebra or pre-calculus, sometimes talking about the even and oddness of a function is just sort of like a novelty, and you kind of like think, well, why am I ever really going to care about that? That seems like a lot of extra complexity. It really saves us a good amount of time in calculus. So we are going to say, and I'm going to make sure I have enough room here, that our total area is going to be 2 times the definite integral from 0 to pi over 4 of big Y, the y value is coming from the cosine, sine function, 2 sine of x minus square root of 2 tangent of x dx. So let's see how this works out. We've got 2 times the integral of sine is negative cosine. So we have negative 2 cosine of x minus the square root of 2. And the integral of tangent, of course, is what? The integral of tangent, in case you forgot, is the integral of sine of x over cosine of x dx. Oh, that's right. The integral of tangent of x dx is negative natural log of the absolute value of the cosine of x plus c, right? Because if our u is, just a little tangent here, if our u is cosine, then u prime is negative sine, and thus we have that negative answer there. So while this is negative, as we integrate and find the integral of tangent of x, we're going to have a sign change there. So plus the natural log of the absolute value of the cosine of x is our answer from that. And then we have an upper limit of pi over 4 and 0. So now we've got, I'm looking at my notes, which were made probably the first year of teaching calculus, and there was a lot more work in there than you really need to be doing, Mr. Taru. So we have 2, stop looking at that. We have 2 times pi over 4 coming in here, and we have 2 times negative 2 cosine of pi over 4 plus the square root of 2 times the natural log of the absolute value of the cosine of pi over 4 minus, now we're plugging in 0, so we have negative 2 cosine of 0 plus the square root of 2 natural log of the absolute value of the cosine of 0. And, you know, we don't need a plus or anything like that. We're doing a definite integral. We've got 2 times negative 2. The cosine of pi over 4 is square root of 2 over 2 plus the square root of 2 times the natural log of the absolute value of square root of 2 over 2 minus parentheses. The cosine of 0 is 1, so we have negative 2 times 1 is negative 2 plus the square root of 2. Now here we have the natural log of the cosine of 0 is the natural log of 1. Well, the natural log of 1 is 0. So we have the square root of 2 times 0. Have I lost count of my parentheses? Okay. So what do we have now? We've got 2 times 2 divided by 2 is 1, so negative square root of 2 plus the square root of 2 times the natural log of the square root of 2 over 2. Don't need the parentheses, you don't need absolute values because that's not negative. Plus 2. Distributing the 2, we have negative 2 square root of 2 plus 2 square root of 2. The natural log, this is 2 to the 1/2. We can clean this up a little bit. The square root of 2 is 2 to the 1/2. And that 2 to the 1/2 is being divided by 2. Well, when you divide like bases, what do you do to the exponents? You divide. So this 2 has an exponent of 1. This 2 has an exponent of 1/2. So 2 to the 1/2 divided by 2 to the first is going to be the natural log of 2 to the negative 1/2 power. And then we can bring that out front and write that as minus 1/2 natural log of 2. Yeah, that's nice. So the natural log of the square root of 2 over 2 is going to get replaced with negative 1/2, so times negative 1/2 natural log of 2 plus, now let's not forget I'm multiplying here, 2 times negative square root of 2 is negative 2 square root of 2. And then we have a positive 2 square root of 2, and we have 2 times 2 is 4. Now with cleaning up this little square root of 2 over 2 here, we have one last step of simplification. 2 divided by 2 is 1, and I can bring this negative out front and say our final answer is negative 2 square root of 2 minus the square root of 2 natural log of 2 plus 4. And yes, we are good. I'm Mr. True. Go do your homework.